Hi, guys. Can I get a sound check?
Hi, can you hear me?
Okay, great. Thanks, guys.
How are you, Professor?
Good, thanks. How are you doing?
I'm doing pretty good.
Hmm. Okay, guys. So first of all, for administrative stuff, how do you guys feel about for the midterm, first midterm to have it on October 5th? Is that, anybody have a strong objection to that? No? Going once, going twice? Okay.
Wait, sorry. Can you repeat that again? Sorry.
Sure, October 5th, it's a Tuesday. So it's not, where are we at today? We're on the 21st, so it wouldn't be next, it's not next Tuesday, it's the Tuesday after that.
I vote October 7th.
Huh?
I'd say October 7th.
What's October 7th? Oh, so now I'm sorry. Did I say Thursday? The Tuesday after that. So not next Tuesday, but the Tuesday after that. Did I say Thursday?
No, I'm just voting.
I think he wants it to be on Thursday.
Oh, you want it to be on Thursday the 7th. Unfortunately, I might be on travel on the 7th, which may not be a problem for you guys, but you'd rather have it on the 7th? Elvis, do I hear that correctly?
Up to everyone though, I don't really mind.
Okay, well, let me check my thing. Let's pencil in the Tuesday the 5th for now. And then I'll see if I can bump it. So I think what we'll cover is the diode circuits and hopefully like bipolar, like transistor information for the midterm. Hopefully it won't be too bad. Okay, so that was for the admin stuff. And now it's just for the, so just a quick review of where we were at. So let me just say that I think what we talked about, and again, I sorry to say the same stuff over and over again, but I think it's important for you guys to have like a overall roadmap of what we're trying to do. So the overall roadmap of what we're trying to do is to describe, a semiconductor device. So at the moment, it's a PN junction, which is the same as a diode. And so this description is like, how does it work? Electrons and holes, dopants, acceptors and donors, and diffusion and drift currents and so on. Then from here we have like we have circuit models. So the next step is circuit models. So one model is our sort of exponential model, where I sub d is, this is V sub d, this is I sub d, where it's I sub s exponential of V sub d over Vt minus 1. And then we have, the constant voltage model. And then the other one, we have an ideal model. So the idea is, so this is, and then using these, we do, solve problems, problems for homework and tests in this class, but what you would be doing it at work, etc., would be to say design / debug circuits. That's sort of like what you'll be using these at work, debug circuits generally. Okay, and so what these are models, and these would be, the exercises, the techniques we're using in solving different types of problems. For example, last time we talked about iterative technique, about how to I think it was Brandon that asked about problem 2.9. That was an example of an iterative technique for calculating an actual voltage and actual current. You need something like that. So that's one sort of a technique to get to a particular set of answers. Then we sort of did so that would be an example of this guy, this type of model and the type of technique you use to use that model to solve certain problems, certain types of problems. Then we looked at sort of a similar circuit, but how to do a rectification. And we used a ideal model in that case. And we looked at going to minus infinity, plus infinity on the input voltage, and looking at the crossover point. That was kind of this ideal model. And this constant voltage model is somewhere in between. Okay, so the goal of the class is not necessarily, it's to introduce you guys to the semiconductor devices, but we're not going deep into that. We're really going into these simplified models and techniques to help analyze circuits. And so we're sort of going through some math, you want to call it tricks, approaches, models, simplifications. We're trying to simplify the analysis and to solve problems. That's the approach. We'll do the same thing when we get to the bipolar transistors. We'll introduce the bipolar transistor, we'll come up with some models for the bipolar transistor, and then we'll go through some techniques to solve those kind of problems. Okay, so anyway, we did a couple of examples of that. There's just like the book is full of examples. The homework is lots of examples. I would like just listening to the lectures or even just reading the book isn't gonna get you there on the test or really to teach you what you're doing. You really have to solve example after example to get familiar with this, which is like what technique you use and where you use what technique and so on. And so you have to do the homework. So that's my suggestion, is do all the examples and do a bunch of the homework problems, et cetera, to get yourself ready. So anyway, that's sort of the gist of over what we're doing. So again, there we have these three models for the diode, and really they're meant to make analysis easier for us, to reduce the complexity of the problem. So again, lots of problem solving. I'm not going to go through all of these, or unless you guys have a specific question about a particular one. Do you guys want me to any particular things stomping you guys, or you have any particular questions about these? Any one of these? Otherwise, I'm going to sort of just move on to the next model. Okay, so that was all the stuff. There's other slides again in the slide deck 3, but it's basically they're just examples of using these models from the book. And I suggest you just go through them. If you run into, there's the answers in the book. The answer for homeworks is on Canvas. And if you have any issues, just sign up for the office hours, and we can go through them together. Okay, so now let's look at another. Whoops, slide deck. This is 42. Let's see. Sorry. Okay, so now again, that was a series of methods to make analysis easier for us. There were 3 different models for the diode. And again, they were trying to show you guys an analysis approach. So here's another analysis approach. And this is called, what we're going to talk about today, sort of as a punchline. Let me just give you guys the punchline before we get started. So just as there is, we're assuming the actual way a diode works is with this nonlinear performance we've talked about over and over again. So basically, out here, the overall equation again is ID is equal to I sub S exponential of VD over VT minus 1. That's the overall equation for this whole curve, describing the relationship between the current and voltage across this diode. So assuming this is the circuit, and this is the diode. And so over here, as V sub D gets very negative, so V sub D gets negative, the approximation is I sub D is about minus I sub S. And again, this I sub S is a constant. And you'll be given that in the problem, or if you buy a diode when you're at work or in the lab, the specification sheet gives you that number, so you can use that. And out here, when V sub D gets positive, I sub D is approximately I sub S exponential of VD over VT. Because you basically get much larger than this minus 1. And then the other thing is this range of sort of permissible V sub D ons, we set as about 650 to say 850 millivolts. Or maybe it'll be, so like for example, if your current is like your I sub D, out here might be, I'm just throwing out some numbers, I don't know, might be like 100 microamps. And out here it might be like, what do I say that it will not violate what I'm about to say next? No, don't hold me to this. Let's say this is 10 milliamps here. Okay, so because we have an exponential relationship of ID with VD, a small change in, here we have a 200 millivolt change in the V sub D voltage, or you could think of it as being like a 30% increase. I don't know what the increase is from 650 to 850, but in terms of the current, because of this exponential relationship, we have a factor of, say, 100 change in current, because again, this is a very steep exponential curve. In fact, a good number to remember is for every, this just drops out of the math, for every delta V sub D, for every time V sub D changes by 60 millivolts, I sub D changes by 10x. And this just comes out of the exponential, the way the exponential works, exponential function. So what this tells somebody is like a very, very small change here gives you a big change on this side. And you have a very small range of voltages before this current just becomes too big in reality, okay? And that's one of the many ways you can use a diode, by counting on it being kind of like a switch. As soon as it hits a certain point, it turns on, and then the devil could be in the details about exactly where the switchover happens and so on. And that's where you get into the details. Okay, so these are, this is the behavior of a diode. And then we said, well, so also another thing I want you guys, this is all stuff that I'm putting here is stuff that you guys should kind of like, and I'm emphasizing is stuff you guys should remember by heart. Another important thing here, which is handy to have in your back pocket, is you can, over here, you can rewrite this as V sub D is equal to V sub T natural log of I sub D over I sub S. It's just rewriting this equation in this form. Sometimes you're solving for voltage and sometimes you're solving for a current. So it's just handy to have both of these guys. And then also remember that also V sub T is a constant. I'm going to put both of these guys in quotes because there's just a constant at some temperature for some particular set of things and is equal to KT over Q. Okay. So so one of the reasons we went to a simpler model for a diode, like the constant voltage model, was that equations, you know, and you guys will see this when you're doing the homeworks, equations that involve a bunch of exponential or natural log terms added to linear terms or other terms are basically usually don't have closed form solutions. They iterative solutions are, you know, painful to do. So you want to kind of find ways to simplify them. So one way was to do this, you know, use the different models for real gross functionality. Okay, like if you want to just know the overall picture of how something works, you can use the say the ideal model or the ideal model or this is the constant voltage model. Which is like that. Or the ideal model, which is this. So this, like I used an example in the previous lecture, was a slide deck 2. Was it? No, slide deck 3. So that kind of approach helps you solve these type of gross functionality. Like it tells you, where were we? Like it has this level of, so this is a general approach where you go to very high differences in V in versus V out. You get kind of this this type of function. What it won't do is tell you exactly kind of what happens around here, like exactly it's what point, like what's the current and the performance at these points. For that, you still have to use this natural log approach, this exponential approach. So today we're going to be talking about something called small signal analysis. That's meant to, it's a simplifying model. Simplify. I don't even know how to spell simplify. I'll give it my best shot. It's a simplifying model of the exponential equation. Okay, so this is the irony of this class and this approach, is all these are supposed to make the model simpler, but it gets really confusing what the heck you're trying to do. I think a lot of like practicing engineers still don't even have a good idea of the small signal analysis or the small signal model. But this is, so I'm sure if you're not gonna be at least a little bit confused, I'll be surprised. So what's the small signal model? The idea is this, that this is, gives you this curve is an exponential, has an exponential function, okay? But for a lot of applications in analog design, you have a very small signal. Like we said, like an audio signal out of a microphone is very small in amplitude of voltage. So like, might be 10, might be 50, might be 60 millivolts. Okay, something like that. And like a lot of other signals in analog domain are also have a very small amplitude. Like think of a cell phone receiver. It's just a very, very small signal that you're receiving. It's just microvolts. It's not even millivolts. So a lot of times what you have is, if I was gonna, so for a lot of applications, a lot of analog applications, the signal is very small. So it might be millivolts, so tens of millivolts, not mega, millivolts to, microvolts. So very small signals. Okay, so if I was going to superimpose that on this analog, on this diode model. So again, if I have this diode, supposed to go through 0. And here it's I sub d is equal to I sub s exponential of Vd over Vt. If I superimpose it here on the Vd curve, it'll be just a tiny change. Let's say I somehow managed to center that signal here around this voltage, like say around 800 millivolts. I managed to somehow center it there, and my total signal swing around there is 10 millivolts. Okay, so if I look at the signal coming out of, say, my microphone, and if I look at it in a oscilloscope, which has a time on one axis and voltage on the other one, it's kind of like the signal's coming out like this with time, which is like, your voice. So this is voltage getting translated to something, but it's only, say, 10 millivolts for the sake of discussion as a peak-to-peak signal. Okay, that means if I draw, kind of superimpose a time graph here, time versus voltage, it's going to look like, so I'm just sort of drawing this, flipping it over, and it might look like something like this voltage, which is what's going into my diode. So the actual input in my diode is just a very small amount around the curve around here. Okay, a lot of applications are like that. So if that is the case, which again, a lot of applications are like that, and we can also force a lot of applications to end up in that situation, what I can do is, again, if it's a very small, narrow region in this exponential curve, I can pretend or make an approximation of this in just this small region, that this exponential curve is actually in just this small region is actually a linear. So replace it with a linear model, i.e. a resistor. So I can actually, because remember, if I was going to draw a resistor on this curve, just for the sake of discussion, it would like a resistor would look like this. So a resistor would have a slope of 1 over R. So if I was gonna pretend just this small area is like a straight line, approximated with a straight line. Again, I'm approximating an exponential function with a straight line just in a small region, then I can just pretend it's like a resistor just in this region. And, or if it's centered here, I could pretend like it's a resistor here. And if it's centered here, I could pretend it's a resistor here. Each one of these resistors that I'm pretending this exponential to be will have a different value. Okay, this can tell that because this curve is 1 over R. So the resistance, if I was going to pretend this to be a resistor here, this is a much sharper slope here than it is here. This will be a much lower value resistor than this. So depending on what kind of resistor value I want it to be, I can try to center this value in different spots. So that's the general idea behind this small signal model. Does that, I don't know, if you have any questions right now, I'm going to go through this. I'm just sort of giving you guys the heads up where we're going. Any questions right now? No? Okay, so let's look at an example. Okay, so let's look into our cell phone adapter again. Okay, so this is a typical problem you'll run into. So this is just as a reminder, this is or the brick or whatever it is that you're plugging into a wall and then plugging the other end into your cell phone. Okay, so one thing, we talked about this front end of this thing looks like, looks like a coil thing which dropped the voltage from 110 volts to 4 volt RMS. Oops. And then we had a rectifier and so on, and we ended up like with some 3.4 volts. This is from, where did we introduce this? So this is like this guy here. Okay, so now we're looking at what happens past this point. Okay, so we've already talked about use a rectification circuit to block off this, make some DC values and then pass on the circuit. Okay, so now we're talking about what happens afterwards. Okay, so let's talk about a case where we need a 2.4 volt DC value here. So need 2.4 volt DC value. This is one way to get that. Okay, so now we said, look, we have each one of these diodes. Notice that we've got the adapter. Let's say this is outputting 3 volt DC out of this end. Okay, so if you have 3 volt DC here, the voltage on these diodes is going to be higher than this point. So these guys are going to be turned on. And each one of them is going to have a VD on of a certain value. Okay, so for the sake of discussion, let's say VD on is 800 millivolts each for each diode. So in other words, if I was going to redraw this with our constant voltage model, it would be 3 closed switches, each one having a battery of 0.8 volts. So if you had this stack up, it would kind of look like that. So the R1 is equal to 100 ohms, and this would be 2.4 volts. Okay, so if you needed a 2.4 volt value here and you had a 3 volt value, you could put three diodes in forward bias and get 2.4 volts here, and this resistor, and then the current here would be enough. I sub X would work out so that you get the VD on in each one of these guys, and then the remainder you have, 0.6 volts left over, and it would just drop across this resistor. Okay, and then the current across this resistor would be 3 volts minus 2.4 volts over 100 ohms, which would be 6 milliamps. Okay, so that's sort of like the overall picture of what this adapter might look like. But then you could run into a situation that if I sub X changes a little bit, for example, what would happen? Your cell phone is going to pull some current, right? Or I sub S you might have a diode with a different I sub S. So I sub S might change. The cell phone might pull some current. So it might not only have the current going here, but you might also have a current going there.
Professor, you had a question.
Yeah.
Yeah,
Thanks.
someone asked if we just assume that it's 800 millivolts, but I would assume to answer that, is that because we're assuming that the diode is fully on and the range, as you previously stated, is from like 600 millivolts to typically 800 millivolts? Is that why you assumed 800?
Yeah, that's exactly, yep. Let me see how else I could put this. Yeah, you pretty much, yeah, I think that's always, so I'm using the assumption that your I sub S is, you started off with a reasonable I sub S value that you would end up with 800 millivolts, given that 6 milliamp current. Let me see how I can do this. So let's say, let's do a couple of examples. Let me see if this will, I'm just pulling this. Let me pull a couple of numbers out of the air and see if it makes sense. Let's say I sub S was 1 times 10 to the minus 10 amps. Okay, so, and then V sub D, let's say I sub X was 6 milliamps, right? V sub D is equal to V sub T natural log of 6 milliamps over 1 times 10 to the minus 10. And V sub T is 26 millivolts. Hopefully this will work out. Feel like I'm doing a trick for the first time here in front of a live audience. Natural log of 26 E3 change sign multiply. Oh, that's not quite work out what I was hoping for. 6. That was not a good number. So let's just do 1 times 10 to the minus 12. See if that's better. I'm getting these small numbers. So for each one, I think I need to assume this thing is actually one like a bigger, let's see, smaller number even. Let me work out the 1, 6. So get a natural log. Let me like work on this example. I'm like getting numbers I'm not expecting. I think I'm just trying to do it live and running into, I'm probably forgetting something. But yeah, just assume they're on, like on with a certain I sub s. Whoops. A certain I sub s value. And the on value, I think it's a good assumption that it's 0.8 volts. But let's say it does end up being 0.8 volts, right? You get the diodes you want, you plug them in, and you get the value. Okay, let me try doing this one more time. Sorry. Let's go the other way. Let's figure out what I sub s would look like. Okay, so let me do this one other way. So V sub D is V sub T natural log of I sub X over I sub S. Let's say that's what we have. So let's say, or I sub D is I sub S exponential of VD over VT. So if I'm saying VD is 6 milliamps, equal to some I sub S exponential of VD over 26 millivolts. So if I do this, I sub S is, and then VD is 800 millivolts. So I have I sub S is 6 milliamps over exponential of 0.8 volts divided by 26 millivolts. That's what I get. Okay, I get 2.6 times 10 to the minus 16 amps for I sub S. So basically, that's sort of that would be our diode. That would be the type of diode we would need with roughly around that I sub S value to get us to 0.8 volts. Does that make sense?
Yes, yeah, that makes sense.
Okay, so now let's say because I don't believe in Should I do this again? I don't know. Maybe I shouldn't, because I don't, I don't have these numbers worked out. So I'm worried about getting into the weeds. But okay, so now let's say this was the case you had, and you ended up at 2.4 volts here, and then you had 3 volts here. Now let's say this, instead of 3 volts here, that from your adapter, you were going to get, you didn't have good enough control over your components, and this 3 volts ended up being 3.1 volt. Okay, so you had a situation where you got 2.4 volts out, okay, with these diodes that you had and this resistor and so on, with the 3 volt output. But the way things work in the real world is there's variations in everything. So let's say you got another adapter, or you plugged it into another wall socket, and you got 3.1 volts out of the adapter. So this is case 1, case 2. So you have a 3.1 volt coming out. Now you've got this issue that if you were going to try to solve the same equation, so you want to see what voltage, that now you have to solve an iterative procedure again, or you have to now solve the iterative procedure. You had this value for I sub s. Okay, so this guy went up by 100 millivolts. And so you have to figure out what was the voltage that dropped across this resistor, and what that means to the new currents. And from those new currents, you would have to recalculate these 0.8 volt values and try to figure out how much this guy changes by. Okay, so you need an iterative procedure, because you'll calculate, you'll have to assume something, right? Let's say assume that this goes from 3 volts to, this goes from 600 millivolt drop to 700 millivolt drop. From there, you need to calculate another current going through this device and figure out what the value is. So let's try to do that, right? So let's say we're just assuming that we're getting like more drop across this guy, right? So this stays at 2.4 volts, right? So assume all extra 100 millivolts drops across resistor. So the resistor goes from having 600 millivolt across it to having 700 millivolt across it. Okay, so now I sub D is going to be 700 millivolts over 100 ohms. This is going to give us 7 milliamps. So basically this I sub X or I sub D changes to 7 milliamps with the same diode we had before. Okay, so now let's see what V sub D is going to be. It's going to be V sub T natural log of 7 milliamps over 2.6 times 10 to the minus 16 amps. So this ends up being 0.804 volts. Okay, which means that if I had 3 of these guys, this would be 2.412 volts at this point, which means that the delta V across the cross resistor is actually equal to 0.688 and not 0.7 volts. So I would have to like start this iterative procedure of, you know, plugging in different numbers for I sub D and seeing if, you know, where that converges between the voltage drop across this resistor and what that tells me about the VD-ons. And we start this iterative procedure to come up with an answer that what happens if this guy goes from 3 volts to 3.1? What happens to the voltage here with the diodes I picked from the first one? Okay, and that's again another time-consuming procedure, and so we want a simpler approach, okay, to do it. And that's where we come up with the idea that, notice in this case, I'm looking at what happens if my voltage changes by a small amount, right? The voltage on my diode in my first iteration went from 0.8 volts, so first iteration, voltage on diode went from 0.8 to 0.804 volts. Okay, so that's really what I'm trying to figure out. Is it going to be 0.801 or 0.805, or, you know, where is my voltage going to land? This is what I'm trying to figure out with this change in this voltage. Trying to figure out where I'll be. So it's a very tiny voltage I'm looking at. So it's a very tiny place in my curve. You know, I have my voltage versus current curve, and I'm like looking at right at 0.8 volts and 0.805 volts, right around this area. So I'm not looking at 100 millivolt, 200 millivolt area. So, which brings us to this approach, which is if I can zoom in, so I can take this diode exponential curve, if I can zoom in to a really small part of this curve. And what is a small area? This is something that is like, you know, we're talking about 10, 20 millivolts, 50 millivolts, something like that, 100 millivolts. So, and again, in this case, we're talking about the voltage changing from 0.8 volts to 0.805 volts. Okay, let's say VD1 is this and VD2 is that. Okay, so a really small amount. That means we've really zoomed into this section. And I'm gonna, if I can do that, I can basically say this is like having a resistor in this section as opposed to being an exponential, because the error in this small section between a straight line and an exponential curve is very small. Okay, so that's the idea behind this, the idea of a small signal analysis. So then I can, instead of having an exponential equation, so this guy, the equation for this curve again is I sub D is I sub S exponential of VD over VT. So that's an exponential equation for this. Let me put that, so for this, just a small area, for just this small area, small length, let's say. I can pretend like I sub d is equal to v sub d, v is equal to over some resistance. I'm going to call that r sub d. And r sub d, what should I call it? Is a estimate of diode resistance over sorry guys, very small range. Okay, do you guys, does that make sense? So if I just look at what this resistance is going to be, this resistance, okay, is just going to be so let's sort of figure out what that resistance is. In effect, we have this is the value, but let's figure out how we calculate that resistance. Okay, so we basically have a situation that we have a change in current over a change in voltage. So we want to basically take the derivative of this curve over here and figure out what that is. So if I was going to look at it from a differential standpoint, okay, I would take I sub d, so di sub d over dvd at vd is equal to vd1 and figure out what that slope is. Okay, that would give me the resistance. Okay, so I sub d is, again, I sub s exponential of vd over vt, approximately. So because I have an exponential, the derivative of id versus vd is I sub s over here. Oh, sorry, it'll just be 1 over VT. So I'm just taking the derivative of I sub d with respect to V sub d. So what this does is it tries to calculate the slope of the curve right here. Okay. So that one basically just brings 1 over V sub t over here, because that's just taking the derivative of an exponential. That's what it looks like. Okay. Now notice that this is just I sub d, right? I sub d is this guy. So when I take the derivative of id with respect to vd, looks like I just get id back divided by vt. Okay, now the derivative of I sub d, let me actually bring it over here. So we got did is equal to over dvd is equal to I sub d over v1. And so just in this small area, this is equal to the resistance, is equal to the 1 over the resistance, or 1 over, let's call it 1 over R sub D. So basically this resistance is just V sub T over I sub D, which is this guy. So what does this mean? Were you guys able to follow what I was doing? I'm just saying, look, if I have this exponential curve, I want to simplify my life by just pretending like this exponential curve is a straight line. Well, you can't just pretend an exponential curve is a straight line. You can only do that if you just look at a very, very, very small area on that exponential curve. Maybe over that really small area, you can pretend like it's a straight line. Now, for each small area, so for example, here, the slope looks like this. If I'd assume the small area is over here, the slope would look like this. And if I assume the area is over here, the slope will look like that. So assuming that I can do that, which I can, in these small areas, if it's small enough with some with some error, I can assume each one of these is a small value, is a resistance, but each area in each location, I'll have to assume a different resistance value. So depending on where I am sitting on this diode, if I was going to do it here, if I had a small voltage perturbation around this point, it would give me a certain resistance. If I was sitting here, it would give me a lower resistance. Notice the slope is sharper. So the slope is 1 over R. And then sitting here, it's a higher resistance. Okay, so for each one of these, in fact, the resistance depends on the actual current across the device. So depending on where I'm sitting here, I get a certain resistance. Here, I get a certain resistance. Here, I get a certain resistance. So if I can calculate what the current is in the diode, I can actually get the resistance just around that neighborhood, just around that area. And then in just around that small area, I can pretend like the diode is a resistor, but just around that small area. And that's called a small signal model. Does that make sense what I just did, guys?
Can you scroll back up just a little bit?
Sure.
Yeah, right. No, yeah.
Let me know when you're good.
Yeah, I'm good.
Okay. Okay, so are you guys familiar with Taylor series expansion?
People did talk about it at some point. I completely forgot what it was.
Yeah, well, so let me just say there's another way to look at this. Okay, so which is through a Taylor series expansion. Don't be frightened. So a Taylor series expansion, it just says that you could take an exponential. So it's just another way of looking at this. So this is what I'm showing you guys is sort of a geometrical look at what we did, right? It just says I'm going to zoom in, and then I'm going to look at the rise over run, and call this 1 over the resistance, right? So it's geometrical look at this thing. So a Taylor series expansion is you can take a function like an exponential. So let's say, so Taylor series expansion. You guys don't need to know this for the class. I mean, for solving the problem, I'm just sort of telling you guys just, because what we're doing is just a mathematical approach to get a simplified model. Okay, so I'm just trying to slice and dice it from a bunch of different ways. So if you do a Taylor series expansion, of e to the x, okay, so you end up with e to the x is equal to 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial dot dot dot. Okay, so if I have like, let's say I want to have this I sub d is I sub s exponential of vd over vt. Okay, so I can do a Taylor series expansion of this thing and get e sub, so this exponential of vd over vt is equal to 1 plus vd over vt plus vd over vt squared over 2 factorial plus vd over vt cubed 3 factorial, blah, 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 blah. Okay, so now if vd over, let's say vd is less than vt, remember vt is like 26 millivolts. Okay, if this is the case, then vd over vt squared ends up being basically a number smaller than 1. Okay, and the smaller vd is compared to vt, the smaller that ratio is, the smaller this number gets. And this is even smaller, right? Because remember, if you take, I don't know, if you take 0.9 and square it, you get 0.81. So it's getting smaller, right? If you take 0.8 and square it, you get 0.64. And if you take, I don't know, 0.25, what am I saying, 0.64. So if I take oops. So the smaller this ratio is, so the smaller VD is, the more, and then also it's getting divided by 2 factorial, which isn't too much, this is a factor of 2, now you're getting to a factor of 8. So basically, the smaller VD gets, the more I'm able to say this doesn't matter, and this doesn't matter. So I'm approximating through this Taylor series expansion when V sub D gets small, meaning that when I look at a small range, so notice this is like it's getting, you know, in a very small range, right? So VD over VT, this delta V that I'm talking about is getting smaller and smaller. I can ignore all the terms in this exponential except kind of like the linear term. Okay, so it's like just another way to saying that that's the approximation I'm making here. It's just a mathematical approximation. I'm saying if I have a very small change in V sub D, I can just assume an exponential is, I can approximate an exponential with a linear. And we can look at it as a geometrical way of doing that approximation, or you can look at it as a Taylor series expansion. But basically that's what you're doing, is you're saying if this change in delta VD is small enough, I can just assume the diode is a resistor. Now, you still, for an overall picture of what your circuit is doing, you still need to keep track of where you're centered. So you still need to know where you are here, and then figure out there's this like a perturbation around it. Okay, so now let's just do a quick example of like how this could be easy. Again, you guys don't like really need to know the details of the calculation. The main thing I want you guys to come out of this from is that the small signal analysis is another simplification technique we're using. We'll use small signal analysis also for bipolar transistors, for MOS transistors, etc. The idea is you're taking some complex equation, relatively complex equation, like an exponential, and you're saying, if I really limit the voltage swing of that exponential, or the area around that I'm moving, like I'm having an input around that exponential, I can, instead of dealing with exponentials and natural logs, I can pretend like that exponential for that, just that small area, the small location, is a linear function. And that ends up being a lot easier to analyze. So that's the main thing, kind of not necessarily how we got there. So for a test, for example, you don't need to derive this function or Taylor series expansion or something. This is just showing us how we got there. The main thing you need to do is, in a test, is, given a certain problem, is being able to kind of realize that you need to figure out where you're centered, the location where you're centered in this diode curve. So you need to know you're kind of centered around here, and then the perturbation around here. This place where you're centered is called the bias point. Okay, because again, you could be here and you'll have a different resistor. You could be here, you could have a different resistance than here. Each one of these is a different bias point, because each one of these gives you a different resistance. So you need to figure out where you are. So you need a bias model, which looks like, just our old type of battery with the large values. It just gives you your I sub D, okay? And using that, you can do the small signal model on top of it. Okay, so now let's go with an example. So let's say we have a diode. Like we had before. And we have a Vn. But let's say this Vn is a function of time. It's not a DC value. And let's say it looks like this. Okay, what does that look like? So as a function of time, it has a offset, which is V0. So it'll look like this. It looks as a function of time, this V sub t that's being applied to this diode. And we want to figure out, as a function of time, what's the current in this diode. Okay. So as a function of time, this guy looks like a bias and a small change around the cosine function, which has a peak value of V sub p. So just basically this equation. And this you see a lot. You see this kind of thing where you have a bias value and a small amplitude around it. See that a lot. So you're putting that in your diode, and you want to find out what your current is coming out of the diode, your I sub D. Call it I sub D. So if I was gonna use, let's say I refuse to use the exponential model, right? Let's say I don't want to have anything to do, sorry, the small signal model, right? So I just want to use the large signal model, right? So you're, say you don't know about, you say you don't know about small signal. What you would have to do is you would have to say, okay, my I sub t is, you know, again, I sub s exponential of Vd over Vt, or, and then this Vd is my Vt, okay? Is V, sorry, not Vt, but V as a function of t. There's a lot of V sub t's going on. V sub t, Vd is Vt is equal to V0 plus Vp cos of omega t. So this is equal to I sub s exponential of V0 plus Vp cos of omega t over Vt. Okay, so now I have to somehow figure out, like for each one of these points, figure out what these values are. Okay, I got to solve a bunch of exponential functions. And notice that basically, so I'm going to have to, as a function of time, I have to plug in values for cosine multiplied by my V sub p, added to my V0, and divide by V sub t, and then get a curve for I sub d. So I'm applying this V sub d to this. So this is this variation across this diode. And then I'm going to get a current coming out of the diode. And I would have to plug in all those numbers into these exponential values. Okay. Now, let's say I really am not, let's say I'm not going to do that, right? I would just use a small signal model that says, because this V sub d is a very tiny swing on this bias point, my diode is going to have just two components. One of them is a current bias. So notice I said I'm going to basically have the diode be a bias and a small signal model. Okay, so I'm going to say my, or so, and do lots of calculations, or with small signal, I just say I of t is my I bias plus small signal value. And the small signal value would be y, so it would be V sub t over, would be basically RV I sub d over, sorry, I sub d. So it would basically be I sub s exponential of V0 over V sub t, because that's my bias point. That gives me a certain I0, okay? Plus I sub s exponential of V0 over Vt over Vt times VP cos of omega t. Okay, so basically I can calculate one exponential value, which is for my bias, which is the same as, whoops, which is the same value I use here. And here I just divide it by v sub t. And then I'm just multiplying it by the cos value. I don't have a whole bunch of different exponential values I need to plug in. I just do it once for the bias condition. That gives me the bias condition. And then after that, it's because I have, instead of an exponential, I model an exponential with a linear curve, and I'm just multiplying that by the input as if I had a resistor of v sub of 1 over this value. Okay, so it's a very much simpler solution to figuring out what the current is with this voltage input than using the full exponential model. Any question about that?
Can you scroll back down for 1 second?
Sure.
So you only calculate the small signal once?
You only calculate the small signal once, yes. Because it's for the small signal is like as if you just need to, it's like you have a resistor as opposed to an exponential thing. So the exponential thing, you still need to calculate your bias point. The exponential model of a diode, you just need to calculate your bias point. But for the dynamic part of it, for this changing part, you just pretend like it's a resistor. You pretend that like just this in this area, your diode is a resistor and you're not doing exponential calculations. You're doing just multiplications. Does that make sense?
Yeah.
Does that make sense, Elvis, or no?
Yeah, it's clear.
Yeah. So I mean, you're still you still have to calculate the different points, but you're not doing exponential. Like you can once you calculate, let's say you get a number for this, right? Let's say this ends up being I don't know, like 6 milliamps, and this is 6 milliamps over 26 millivolts, right? And this is 10 millivolts cos of omega t. So, you know, it ends up being like you can start kind of doing these. I mean, it won't be a lot of fun, but you can kind of start doing this stuff in your head pretty much, or trying to like figure out what the curve would looks like as opposed to an exponential. If this was an exponential, you'd have to, you know, we don't have field for exponential numbers that we're plugging into an equation. So you'd actually have to plug it in and get different values each time. Any other questions, guys? Okay, well, I'll talk to you guys on Thursday. Take care.
You too, Professor.
Professor, I had some really quick questions.
Sure, go ahead.
How many questions were gonna be on the midterm?
I'm gonna guess like maybe 3 or 4, something like that.
Okay, and how long would we have to complete the midterm?
I'll give you guys like 24 hours. So I'll put up the midterm at 5:30 on Tuesday, assuming I won't move it. Well, I'm checking for Elvis to see if we can move it to Thursday, but let's say it's on Tuesday. I'll put it on up on 5:30 p.m. on Tuesday evening, and you have till Wednesday at 5:30 p.m. to email it back to me. Email your results back.
A question that adds on to that. Would you tell us like what model to use, or if we like we use like small signal or something?
Yeah, I'll give you guys pretty good guidance on what to use.
Okay.
Yeah.
So Professor, would this test mainly be on chapter 2 and 3? And then like that's like on the textbook?
Yeah, I might be we'll see how much progress we make, but mainly on 2 and 3. I might put some on 4, but we'll see how much progress we make.
All right, thank you.
Sure. And it's of course open book, open, whatever you guys need to use.
I also had another really quick question.
Sure.
Can we use like a tablet or something to write out our work, or does everything have to be handwritten, like with a pencil?
No, it just has to, end result just has to be PDF sent in.
Okay.
That's it.
Okay.
And then, I just have to be able to see the steps,
Mhm.
your thinking, units and all that good stuff. But you could write it down, take pictures of it, scan it in, or use a tablet, whatever you like. Just the end product, I just need a PDF.
Okay, for sure. Thank you.
Sure. Anything else, guys?
Thank you.
Okay, take care, guys. Bye.
Thank you.
Thank you, Professor.
Thanks.